Hi again. Today's lecture is section 13.3, where we discuss the concepts of arc length and curvature. And in this video, the first part of section 13.3, we're just going to talk about the arc length. Okay, so what was the arc length, right? If we have, what we know so far, if we have a plane curve, right? And I want to know how much is the actual length from A to B, how much is this? The length of this curve, and let's say that this curve C is defined as x is equal to f of t and y is equal to g of t, parametric curve. Then the length S was equal to the definite interval from A to B, square root of dx dt squared plus dy dt squared, and this is integrated with respect to t, of course. So this is what we know from the previous chapter, right? We extend the same idea when we talk about vector functions, okay? So let us say that R is the vector function defined as x of t, y of t, z of t. This is a vector function, r of t, of course. Then the arc length evaluated from A to B is the definite interval from A to B of the square root of dx dt squared plus dy dt squared plus dz dt squared, all of that integrated with respect to t. Okay, so this is basically a just an extension of what we knew previously, right? Or if you want to have written this as r of t is equal to f of t, g of t, h of t, right, the same thing, then the arc length is going to be the definite interval from a to b, square root of the sum of the squares of the derivatives f prime of t squared plus g prime of t squared plus h prime of t squared dt. Okay, very, very simple concept. Okay, that being said, we can do the first example. Example number 1. Find the arc length of the curve represented by r of t is equal to 3 sine of t, 3 cosine of t, and t from the point with coordinates 0, 3, 0 to the point B with coordinates 3, 0, pi over 2. Okay, so first of all, going back to the formula, right, I know that the arc length is the definite interval from A to B square root of f prime of t squared plus g prime of t squared plus h prime of t squared dt. Okay, so the first thing that I want to point out is that I'm integrating with respect to t. That means that a and b are the end and the initial and the end point of the interval where t runs. T runs from A to B. And here in the problem, basically, we have to discover for what t we start from the point A and for what t we finish at the point B, right? Well, what would be the easiest point to check that? Well, look at the third component of the vector function that actually spells it out for us. So t, when t is 0, right, all the way to when t is pi over 2. because the third component of this vector function, right, describes the point A when t is 0 and describes the point B when t is pi over 2. Of course, it's very easy to check whether that's in accordance with the other two components. When t is 0, sine of 0 is 0, good. Cosine of 0 is 1, times 3 is 3, very good. When t is pi over 2, sine of pi over 2 is 1, times 3 is 3, cosine of pi over 2 is 0. Okay, so first of all, I know how much is A. A is 0 and t is pi over 2. Next thing I want to do is find how much are f prime, g prime, and h prime, right? And those f, g, and h correspond to the parameters of the vector function. So f of t is equal to 3 sine of t, which means that f prime is equal to 3 times cosine of t. G of t is equal to 3 cosine of t, which means g prime of t is equal to negative 3 sine of t, and h of t is equal to t, which means that its derivative is equal to 1. Okay, so now the sum f prime of t squared plus g prime of t squared plus h prime of t squared is equal to 3 times cosine t squared plus negative 3 sine of t squared plus 1 squared, right, which is 1. And now we get 9 times cosine squared of t plus 9 times sine squared of t plus 1, which is equal to 9. I factor 9 for these two terms. I get the standard, most basic trigonometric identity. Cosine squared plus sine squared is 1. 9 times 1 is 9. 9 plus 1 is equal to 10. So now I can go back to my, to the arc length definition. So the arc length when t goes from 0 to pi over 2, from 0 to pi over 2, square root of f prime of t squared plus g prime of t squared plus h prime of t squared, and that's, I've evaluated that's equal to square root of 10 dt. Interval of a constant is just square root of 10 times t evaluated from 0 to pi over 2, which is equal to square root of 10 times pi over 2. We can do another problem. Example number 2. Calculate the arc length of the vector function r of t is equal to t cosine of t, right, t times cosine of t, t times sine of t, and 2t for t on the interval from 0 to 2 pi, right? The difference between this problem and the previous problem is that here the beginning and the end of t is given with respect to t, not defined as the starting point and the end point on the curve. Okay, so again, s is equal to the definite interval from 0 to 2 pi, square root of t times cosine of t prime, and then we square that, plus t times sine of t prime, then we square that, plus 2t derivative of 2t squared, and then we integrate with respect to t. It's equal to the integral from 0 to 2 pi square root of 2. In both derivatives here, be careful of the product rule. So derivative of t is 1, so only cosine of t minus t sine of t, y minus, because derivative of cosine is negative sine, so this squared, plus derivative of t times sine of t is derivative of t is 1, so only sine of t plus derivative of sine is cosine, t times cosine of t squared, plus derivative of t is 1, so that means 2 times 1 is 2 squared plus 4 dt is equal to the definite integral from 0 to 2 pi. And now you expand these two terms. That's cosine squared of t minus 2t cosine t sine t plus t squared sine squared of t plus, now the second term, sine squared of t plus 2 times t cosine t sine t plus t squared cosine squared of t, okay, plus 4 dt. Okay, here we cancel the terms that we can cancel, and we concentrate on what we can simplify. We can simplify this term right here. This term right here gives us only 1, so that's equal to from 0 to 2 pi cosine squared plus sine squared is just 1, plus t squared sine squared t plus cosine squared t plus 4 dt, and that's equal to the definite integral from 0 to 2 pi square root of 5 plus t squared dt. Okay, now as you can see, and this is why I chose this problem, and actually we're very lucky if we get this kind of problem. We get to an unfriendly integral, let's put it that way. So if you solve this starting with using trigonometric substitution and so on, you would get the following answer. So I'm just going to give you the answer, and then you can figure it out by yourself later on if you want. 2 pi square root of 4 pi squared plus 5 ln of 2 pi plus square root of 4 pi squared plus 5 minus pi over 2 ln of square root of 5. So this is the answer to this definite integral. And why did I chose this integral is because I want to point out that in real life it is very, very rare, extremely rare, that you are going to get a function such that you would be able to evaluate this integral in terms of elementary antiderivatives, okay? And even if you are lucky to do so, you would expect something like this as an answer, okay? So usually in real life you would have to use a some kind of software to evaluate this, and those software usually work on basis of approximation. But as even when we were doing arc length functions in Cal 1, we have to give you questions that are suitable, that are made for these types of questions. So the square root in the integrand makes it very, very difficult for these antiderivatives to be actually evaluated in terms of elementary antiderivatives. Okay. Now we go back to the arc length definition. So the arc length is derivative from A to B, square root of f prime of t squared plus g prime of t squared plus h prime of t squared dt. But I want to point out that this square root here is nothing else, right? Where, oops, sorry. F of t, g of t, and h of t are the components of this vector function. Now recall that the magnitude of this vector, this is the magnitude of the derivative of the vector, right? So r prime of t is equal to f prime of t, g prime of t, h prime of t, and then the magnitude of the derivative is equal to the square root of f prime of t squared plus g prime of t squared plus h prime of t squared. Okay. Now notice this. Notice the definition of this expression is the magnitude of the derivative vector, okay? Which gives us what? Gives us another expression of the arc length, and that's the definite interval from A to B of, and now instead of writing this down, we can just write the magnitude of the derivative of the vector function. And you will see very, very soon how handy this expression is going to become. Okay? Okay, now we're going to talk about the arc length function. Okay, so what happens? What is the arc length function? Arc length function is if I have some space curve and I want to start evaluating the arc length from the starting point, right, all the way to some t, or better said, to any t, right? Then we can write the arc length as a function where it starts from the point A, but then this here is going to be a variable, right? We can put any t where t is greater than A. Okay, this is the arc length function. Okay, by the fundamental theorem of calculus, what will happen if I take the derivatives on both sides, right? If I have d dt of s of t is equal to d dt by the fundamental theorem of calculus, the derivative of the arc length function ds dt is equal to what? I hope that you remember. This is just the derivative of the integral, brings us back to the integrand, right, to the function itself, r prime of t. Again, a very useful expression that we're going to see later on. Okay, let's continue working with the arc length function. Okay, the next topic is going to be arc length parametrization. Okay, so what did we say? We said that if I have we can change the variable t, right? For example, the if r of t, right, sometimes I put this arrow here, sometimes I don't, is equal to t squared t cubed. We'll work with this curve later on, where t goes from 1 to 2, describes the same curve as r of u, where I have e to power u, e to power 2u, e to power 3u, where u runs from 0 to ln of 2. So basically what we have done here, we have substituted e to power u is equal to t. Okay. Now we're going to talk about reparametrization with respect to the arc length. Why? Imagine if you take a stroll, if you go in a park, right? How are you going to describe your path? You're going to describe if you start walking over this path, right? You want to know after this much, you want to describe this point right here with respect to how much distance you have covered all the way up to here. We don't describe our point in space always by the time. Sometimes we described our point by the length that we have passed, right? So basically the question is, can we reparameterize our curve from with respect to t to write it down with respect to the arc length? Okay, that will depend on whether we're able to express whether we're going to be able that will depend on whether we can express s as a function of t, okay, or better said, t as a function of s. For example, okay, reparameterize r of t given as 3 sine t, 4t, 3 cosine of t with respect to the arc length measured from t equal to 0 in the direction of the increasing t, in the direction of increasing t. Okay, so if I'm able to express t as a function of s, then it's very easy. Here we're going to put s, and we're going to instead of t, we're going to put an expression in terms of s, and we're going to substitute it here, here, and here. Okay, in order to do that, first of all, what do we have to do? We have to figure out how much is the arc length function. By definition, this is the definite integral from 0 to t, the magnitude of the derivative of the function. So let's see how much is that. This is the definite integral from 0 to t, square root of, well, here on the side, this is going to be equal to 3 cosine of t negative, sorry, 4 and negative 3 sine of t, okay? So that's the derivative. The magnitude is square root of the sum of the squares of the component, so 3 cosine of t squared plus 4 squared plus negative 3 sine of t squared dt, which is equal to the definite integral from 0 to t square root of 9 cosine squared t plus 16 plus 9 sine squared t dt, which is equal to the definite integral from 0 to t square root of, what can we simplify here? Factor 9 for sine squared and cosine squared. Cosine squared plus sine squared is 1. 1 times 9 is 9, plus 16 dt. So you get the definite integral from 0 to t square root of 25 dt. Integral of the constant is, so just here I have, this is equal to 5 t minus 0, which is 5t. Okay, so what do we have? I have s is equal to 5t. Okay, from here we can conclude that t is equal to s over 5. So if we are able to solve this definite integral and we are able to express t as a function of s, I can express the vector function with respect to s. And don't forget that s is the arc length parameter. So r of s is equal to, you have 3 sine of t, t is s over 5, so that's 3 sine of s over 5, 4 times s over 5, and 3 cosine of s over 5. When t is equal to 0, when t is equal to 0, when t is equal to 0, s is equal to 0, so starting with s is equal to